Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C, grade 11 college math, and I'm the teacher, Bronwyn Slate. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM and also on the television at Bell Express View channel 972. You're always welcome to join me live through the Zoom link, which is available both from me, your teacher, and also your DEC. Our classes are scheduled from Monday through Thursday, 2 until 3 in the afternoon, and we are in our third week of our 9-week course. You should be starting to think about submitting some work for marking. So a reminder that the support questions, the ones with the pencil icon, are not for marking. You decide which ones and how many to do. But if you're understanding a concept, feel free to skip questions. It's fine. You don't have to do them all. If you'd like more practice, let me know about that, and I'm happy to send you more practice so that you have what you need. The answers are in the back of your workbook, so please check your work. This way you know if you're on the right track or if you're struggling with something and you can ask me questions. It's there for you to use. The key questions, the ones with the key icon, are the ones to submit for marking. So please do all of these questions, showing all of your work, your steps, your thinking. This way I can understand what it is that you understand and help you set you up for success. So how do you actually submit your work for marking? Well, there's 3 methods. The first method is to scan your work and send it electronically. If you have a device, you can scan your work using Apple devices using the Notes app and Android devices using the Google Drive app. These are free apps that come with these devices, though they also can be downloaded if you need to. On my YouTube channel, I have some tech tutorials that walk you through how to actually scan with these devices. So check those out if you need help. If your only option is to take pictures, it's fine to send me pictures as well. The files are just a bit bigger and potentially more awkward to send, but that's fine if that's what you need to do. So then you can send it to me either by email at studentwork@nnec.on.ca and CC it to me at bronwyn.slate@nnec.on.ca, or you can send it through Facebook Messenger, where my name is B. Slate Wahsa. The second method is to drop your work off in Sioux Lookout. We have an outdoor mailbox at our location at 74 Front Street. We are the bright red building next to the post office, and we have a small white mailbox next to our side entrance. So just put your work in there anytime, and I will get it back to you as soon as I can. The third method is to hand your work into your DEC. Your DEC can either send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. Students are also welcome to fax their work if that is something that makes sense for you to do. If you'd like to connect with me on social media, both my Facebook and my YouTube channel are under the name B. Slate Wahsa. You can friend me on Facebook or subscribe to my YouTube channel, and then you'll get notifications every time I upload one of our videos. All of our radio Zoom classes are recorded, and I upload them shortly after airing to my YouTube channel. They're all there under a playlist called MBF3C, which is our course code. Then also there are short videos that explain common errors and confusing concepts that are there that can support you. So go check that out if you need some help. Math is a really visual subject, so I strongly encourage you to access the videos. They are going to set you up for the most success to really understand what it is that we're talking about. If you can't join us live through the Zoom link and you can't listen to or watch the YouTube replays, let me know, and I'm happy to send you a copy of the recordings if that would be useful. So if you do have any questions or concerns, please reach out, connect with me. My email address is bronwyn.slate, and that's spelled BRONWYN @nnec.on.ca. My Facebook is B. Slate Wahsa, You can call me at the office at 807-737-1488, extension 2209, or toll free at 1-800-667-3703. My office hours are Monday through Friday, 9 a.m. to 3 p.m., though I teach the last hour of my day, so that's not a great time to try to get a hold of me. All right, lesson 5, we are wrapping up unit 1 and with lesson 5 today, and that is on simple exponential equations. So our learning goals for today are that at the end of this lesson, you'll be able to sketch by hand the graphs of simple exponential functions, and you'll understand the key properties of exponential functions. You know that you've met these learning goals because you can visualize and sketch exponential graphs. You can explain how to identify an exponential equation, and you can explain the similarities and differences between exponential growth and decay. So answering the question, when will you use this in real life? Well, we're discovering how the world around us makes sense. So there's math all around of us, even if we aren't necessarily recognizing that or paying attention to it. But it plays a large part in our role. And so understanding how to see those things that are happening around us can help us be more informed and make choices in our lives. But first, let's activate our brain with some mental math. I don't believe that Mad Math Minutes strengthen anybody's ability to do math or anyone's comfort. They just really focus on rote memorization and speed, and those aren't really important skills when it comes to true math education. So instead, we work in our class about developing strategies that we can use in various situations that help us become comfortable with numbers. So our question today is 9 times 16. And we're going to use the strategy of breaking factors into smaller factors. So remember, just like we've been doing with factors before, factors are the numbers that multiply to be your product, to be your answer. So here, if you don't know what 9 times 16 is, what you can do is you can break your numbers up into their factors and maybe rearrange them so that they might be more friendly. So 3 times 3 is the same as 9. 9 is the product of 3 times 3. And 16 is the product of 4 times 4. So because we know that multiplication is commutative, which means that we can do it in any order, we could rearrange these. And we could say, well, 3 times 4 times 3 times 4 is the same thing as 3 times 3 times 4 times 4. And 3 times 4 is 12. And 3 times 4 is 12. And 12 times 12 is 144, which is one of my facts that I know comfortably. And so that means that 9 times 16 is also 144. So this isn't necessarily always going to be the best strategy. You might not end up having factors that are more friendly, but sometimes they work out that they are able to make your life a little bit easier. So if that's true, then go for it. All right, what do we need to think about before we dive into today's lesson? So I just want to make sure that we understand exponential growth before we start to analyze it too much. So we're going to use the example of doubling. And this means that for every 1 time increase, our amount of things double. So we're going to compare our graph. So here on our horizontal axis, we have our time. So that means that we're increasing by 1 hour or 1 day, and then 2 days, and then 3 days, and then 4 days, something like that. And then the amount of whatever our stuff is that's doubling. So maybe it's bacteria, maybe it's money, who knows? But we're just comparing it. The idea is that for every time that increases, our amount doubles. So on day 0, we have to start with something. So on day 0, we have 1 thing. So then on day 1, now we have 2 things because that 1 thing doubled. And on day 2, now we have 4 things because the 2 things from day 1 have now doubled. So we have 2 new things. Day 3, now we have 8 things because the 4 things that we had on day 2 all doubled. On day 4, now we have 16 things because the 8 things that we had on day 3 have doubled. So as you can see, this really, really quickly, you end up with a lot of stuff. As we continue, if we were to do 16 things doubled, we would get 32, but that just goes off of our page and we don't have any more room. So, but that just shows us how fast exponential growth increases and how it works is that we're doubling for this example. When we're doubling, it means that every time, every new day, we have twice as much as we had the day before. Then we also want to understand what exponential decay is. So exponential decay is when we're cutting our amount into a fraction. So we're going to use the example of 1/2. And this means that for every time increase, we're cutting our amount in half. So we're starting with a bunch, and after 1 day, we have half as much as we had yesterday. And then after 2 days, we had half as much and after 3 days, we have half as much. So that's how a half-life works. With exponential decay, any sort of fraction so it doesn't have to be a half. It could be a quarter. It could be 3/4. It could be 90%. But it's something less than 100%. So again, we're going to compare time to amount. This time we're going to start with a lot. So on day 0, we're starting with a lot. We're starting with 16. And by day 1, we have cut that 16 amount in half. So we've lost half of the amount. So now we have 8. And on day 2, half the amount of day 1 is 4. So we cut that away and we're left with only 4. And on day 3, half the amount of day 2, which was 4, we lose. So that was 2. And so now we're left with 2. And then on day 4, half the amount that we had on day 3, which was 2. So we have half the amount of that is 1. We're left with 1. So exponential decay, you can see as time moves forward, we get less and less. So we're getting smaller and smaller. And that's what exponential decay is. All right, so let's dive in with our new concepts and moving on from just understanding what growth and decay are, how do we manipulate, how do we learn from that? So I just wanted to show first where this is around us, because this is another one of those examples that a lot of information is analyzed using exponential growth and decay. So here I have 4 graphs on my screen just to show you. So we have on this one in the top left, we are comparing the initial price of a vehicle to the mileage, to the number of kilometers driven. So this is showing us how vehicles depreciate, how vehicles lose value. So the lines on that are for various types of vehicles. But generally, you can see that they all very quickly, after not driving very much, you're losing a lot of value really, really quickly. And then that slowly levels off and slows down. And so that is exponential decay. How valuable your vehicle is could be modeled by an exponential decay graph, because it starts off really high and then you lose a lot really, really quickly, and then that slows down over time. Here in the top right, we have the number of smartphone users in millions. So we're comparing Android and Apple, and you can see this isn't like a super beautiful curve, but it has the same sort of idea. So Apple slowly starts and then gets bigger and bigger and bigger, bigger and bigger and bigger, kind of on a curve sort of idea, this gray line. It's a slow curve. And whereas Android starts off really, really small, and then in 2009, it jumps up, and then in 2010, it just increases much, much faster. So it's an exponential growth with a higher degree, or not degree, but higher base, really. So we're going to look into how we can figure out what these different shapes how they exist. the forgetting curve, which we talked about on Throwback Thursday, and how fast we forget information and how if we review it, we don't forget it as quickly, is an exponential curve. So we start off knowing a lot, and then we very quickly forget things, and then over time it slowly levels out. And another place where it comes up really recently was when COVID-19 first was getting to be known worldwide, and the number of cases were getting to be tracked. So this is just, this graph is comparing days after March 1st in 2020, because that's sort of when the pandemic became a little bit more known and discussed worldwide. So here, after 5 days, the number of cases we can see is about 5,000. By 10 days, it's almost at 10,000. By 15 days, we're at 15,000. Then by 20 days, we're at 30,000. At 25 days, we're over 60,000. So very slowly it was increasing, but then all of a sudden it curved right up. So that's an exponential growth, is that it increased, it got faster and faster and faster, and got higher and higher and higher. So that would be exponential growth. All right, so this is on page 30 of your IEL booklet. And so we're going to understand exponential functions. So we just looked at all those graphs that explain what are representations of exponential growth and decay, but understanding those actual functions, what those lines mean, and how we can affect them is important. So an exponential function is the mathematical model that describes either exponential growth or decay. These are our two options. It's either getting bigger or it's getting smaller. The formula, or the general form for this, is y equals capital A times b to the exponent x. And b is the only part that has the exponent x. So b is called the base, and this can be any positive number except 1, because 1 to the exponent anything is always 1. So you don't have a growth or decay. Then a is called a scalar, and this can be any non-zero number. So this, if it's 0, the whole thing is 0, so that's not helpful, but this can be any number. Just like when we had parabolas, we had that a at the beginning in terms of things making wider or reflecting them. This is the same idea. Then we have x, which is our input number, the number that we control. So that's like our number of days or time moving forward. And then we have y, which is our output, which is our result number, which is what we're trying to learn about. So a key to an exponential function is that it always has a variable in the exponent. So for example, we have d equals 8.25 to the exponent t. So we have exponent t. Yes, that's an exponential function. Then example 2, we have y equals 2 to the exponent x minus 3 plus 1. Here, x still is in the exponent, so we still exponential function. And then we have c equals -6 times 0.33 to the exponent n. Again, n is our exponent in our, n is our variable in our exponent. Again, an exponential function. So some non-examples, some things that are not exponential functions. Y equals x squared plus 5x plus 13. We do not have any variables in our exponent. We have a squared, we have an exponent, but it's not a variable, therefore it's not exponential. Our second non-example is p equals 128i minus 93. Again, no variables in exponents, therefore not exponential. And then our third non-example is w equals x to the 4th yz cubed plus x minus 2y plus y 0.5 z. So again, lots of variables, but no variables in the exponent. Therefore, this is not an exponential function. Okay, really, variable has to be in your exponent for it to be exponential function. That's what has to be changing. We can control. So there are several properties of the graph of all exponential functions. So some things about exponential functions, that's always true. So when your base is greater than 1, this is exponential growth. So here is an example on a graph, a function. Here we can see that our red line, our curve is getting bigger as our time increases along our horizontal axis. As our time increases, we gradually, it's very gradual to start, and then it goes up really, really quickly, and that's exponential. So as x increases, y increases. So then our second property is that when b, our base, is between 0 and 1, so is a fraction or decimal, this is when we have exponential decay. So here is the graph. You can see it is a mirror reflection. You can see, so now as our t increases, our time or horizontal increases, our vertical, our y, decreases. We're getting smaller and smaller. So we're starting really high and we're getting smaller and smaller. Then our third property is that when a is equal to 1, all exponential graphs will go through 0, 1 or 0.01, right? Because if we're multiplying our base number to the exponent 0 times 1, we aren't stretching this in any way, then our base, no matter what our base is, to the exponent 0 is always going to equal 1. So it's always going to equal to be 1. So every single exponential function that doesn't have a scalar, isn't being stretched or compressed in any way or reflected, it always goes through 0.1. So here you can see I have 6 different exponential functions on my graph, and they all run through 0.01. And then also the other property is that there is no x-intercept because y never equals 0. So we are always getting closer and closer to our x-axis, but we never cross it. Because if you think about it, in order for, that would mean that something would have to be, x would have to be 0 at some point, or sorry, y would have to be 0 at some point, and there's no way to multiply 2 numbers by themselves and get 0 unless one of those numbers are 0. And if that means that we don't have any stuff that's either doubling or increasing or nothing that's cutting in half. So you always have to have something to start with if we're going to double it or whatever the base is, or we have to have something. If we're cutting something in half, we're always going to be left with something. This is one of those, like, it moves on to infinity ideas, but we never actually cross your x-intercept for an exponential function. So now you should be able to answer questions 1 and 2 on page 32, where you're just understanding those fundamental properties of exponential functions. I want to now talk about those 2 key exponential functions, doubling time and half-lives. These are the ones that come up most frequently, and they are sort of the most fundamental exponential functions. Everything else you can modify these 2 and you can generally understand them. So first we're going to look at doubling time. And again, this is the time it takes for a quantity to double in size. We use this example, but I just wanted to define it a little bit further. The general form for this is P equals P sub 0. So this is like, I'll define them in a second, times 2, and 2 is the exponent T divided by D. So let's define those variables. So P represents the final quantity. P0 represents the initial quantity. So that 0 is like, the sub 0 is saying that this is where we're starting. Like, again, ground zero. That's what, like, if you're at a detonation or an illness or something, ground zero is the point of where it started from. Then T represents the time. and D represents the doubling time. So how long it takes for your quantity to double. And then your base is 2, which indicates it's doubling. So for doubling time, your base is always going to be 2. If you want to do tripling time or quadrupling time or increasing by a factor of 10, then that would change your base. That would change the 2. If you was tripling time, it would be 3. If you were quadrupling time, it would be 4. If you were increasing by a factor of 10, it would be 10. So for doubling time, it's always 2. But if you want to increase at a faster rate, then it was a bigger number, then that number would replace the base number, the 2. Half-lives are the opposite, the reverse. So this is the time it takes for a quantity to decay to half its original amount. So the formula for that is M equals M0 sub 0 times 1/2 to the exponent T over H. So again, M represents the final quantity, how much you have at the end. M0 represents the initial quantity, again, how much you had at ground zero. T still represents the time, and H represents the half-life, so how long it takes for something to cut in half, to lose half the amount. And then the base is 1/2, which indicates that it's a half-life. So again, if you wanted a third life, then it would be 1/3. If you wanted a quarter life, it would be 1/4. If you wanted a 100th life, it would be 1/100. But half-lives are something that comes up in general pretty frequently. So let's look at a practice problem and understand how this actually works in the context of a real life example. So E. coli is a very harmful type of bacteria that can be found in meat that is improperly stored or handled. The relation N equals N sub 0 times 2 to the exponent T over 20 estimates the number of E. coli, which is your N, of an initial sample of N sub 0 bacteria after T minutes, T being your time, after a certain number of minutes, at 37 degrees Celsius, which is body temperature, under optimal conditions. So this tells us how quickly something doubles, how quickly the E. coli bacteria doubles, because 2 tells us that it's doubling time, right? Our base 2 tells us our doubling time. So we know we're talking about that this is getting more. So part A, what is the doubling time of E. coli? So we know that N is our final amount, N is our sample, N sub 0 is our initial amount, it's how much we started with. 2 is our base, because it tells us that we're doubling. T is our time, how long it is that we've been doubling for in minutes. And 20 is our doubling time. So 20 minutes, because T is in minutes, so our doubling time is also in minutes. 20 minutes is how long it takes to double. We'll say long it takes E. coli to double under optimal conditions, but we won't write all that out. It's not like if it was colder, or this is just like ideally for that bacteria, not ideally for us, but ideally for the bacteria, it would double in every 20 minutes. So for part B, if a sample of E. coli contained 5,000 bacteria, how many will there be after 1 hour? So we're going to use our formula here. So we're looking for N. We're trying to figure out the total in an hour, total at the end. Our N0, our initial amount, is 5,000. And our T is equal to 1 hour, but we want T in minutes. So if we want T in minutes, that means that we're going to talk about it in 60 minutes. So to figure out our N, how much we have, we're going to do, I like writing down my formula every time so that I know that I have all the parts, or if I make a mistake, we can see where I made the mistake. So we have N is equal to 5,000 times 2 to the exponent 60 over 20. And that is equal to, and we can just use our, not what I meant to do. We can just use our Desmos calculator. You can use a calculator. You can do this in parts if you want to, but I'm also totally fine with you just using your calculator. So 5,000 times 2 to the exponent, and then you may have to put your 60 divided by 20 in brackets in your exponent to make sure that it does it properly. That's something that you need to figure out with your calculator. So if we do that calculation, that is 40,000 bacteria. So how many will there be after 1 hour? There will be 40,000 E. coli bacteria after an hour. I don't know how to spell bacteria. My brain just, don't know what I was spelling. Something with 2 T's. So that is pretty quick, right? Going from 5,000 to 40,000 in 1 hour because you double every 20 minutes. So part C, if a sample of E. coli contains 1,000 bacteria, how many will there be after 1 day? So we have less bacteria, but we're doing it for a longer period of time. So again, we're going to list what we know. So we have our sample is 1,000 and our time is 24 hours, but we want that to be in minutes, right? So we're going to do 24 times 60 to figure out how many minutes that is. So 24 times 60, well, 24 times 6 would be 20 times 6 is 120, and 4 times 6 is 24. So that would be 144 times 10 is 1,440 minutes. Okay, so we're going to put it into our formula. So we have n equals n sub 0 times 2 to the exponent t over 20. So that means that we have 1,000 times 2 to the exponent 1,440 divided by 20 in our exponent. So doing it on our calculator, again, 1,000 times 2 to the exponent, and put in brackets 1,440 divided by 20. Oops, put in 30, 20 is equal to 4.72 times 10 to the 24th. So there will be, so times 10 to the 24th means that we need to move this decimal place over 24 places. So that's just a incredibly huge number. So we don't need to take it out of scientific notation. We can just leave it in that form. So this is why E. coli bacteria is really concerning, because it grows super, super fast. And that's how we can understand doubling time. So an example of understanding half-lives. So the relation t equals 190 times 1/2 to the exponent t over 10 can be used to determine the length of time, which is t in hours, that milk of a certain fat content will remain fresh. Capital T is the storage temperature in degrees Celsius. So part A, what is the freshness half-life of milk? So how long is it and the milk is fresh? So remember, our half-life is the number that we're dividing our T time by. So that is 10. So we have to say, is it 10 minutes? We look back and we say, well, time is measured in hours. So that means our half-life is also measured in hours. So 10 hours is the how long until your milk at storage temperature. So this is like at room temperature. or this is what we're looking at. So we're going to graph this relation, and I'm going to show you how to graph it on Desmos. So Desmos has a scientific calculator, but they also have a graphing calculator. So if you go to desmos.com and then you go under Math Tools, Graphing Calculator, you will get a graph. And then over here on your left, you can put in your whatever it is that you're talking about. I can't remember if you have to do it with Y and X, but let's see. So if I just put in our formula that we have in our question. So I put it in, and if we look, my graph, it says, well, there's nothing there. It's because I'm zoomed in really close. So I'm going to zoom out, and we don't have to do it X and Y. We can use our variables that were in our question, but I'm going to zoom out, and we can see now what our graph looks like. So you can use Desmos to help you get an idea roughly of what it looks like. So we were expecting its half-life, so we're expecting it to be decay. That makes sense. With sketching, I don't need it to be exact. We are just getting kind of a rough idea. So in your Desmos, you can also get all of the points in here. Let me show you how you do that. And when you go to Desmos here, if you click on this little gear symbol, you can, and then click on the table of value symbol, you can get all of your table of values. If you want a table of values, that's when you have to put in Y and X, or else for some reason it doesn't. I'm pretty sure. Yeah, it won't give you your values unless you have X and Y. Just it's the way that the program is written. But that's not really important. And then you can also extend it in terms of which ones you actually want. So you can see I've done that, and I've picked a bunch of values and gotten a bunch of values. And then I've gone through, and you can graph those values to give yourself that sketch of what it would look like. So Desmos is totally your friend. Feel free to use it to graph things. There are apps that you can use on both devices, on both Android and Apple devices, that I'll link in the show notes so that you can check those out if you're interested in. So then, how long will milk keep fresh at 22 degrees Celsius or at 4 degrees Celsius? So we can use our graph to answer these questions. So we're comparing our time to our temperature. So if we're interested in figuring out how long milk will keep fresh at 22 degrees Celsius, so that means that we look on our graph and we find 22. So here is 20, and we can see that it goes up by twos, right? 20, 22, 24, 26, 28, 30. So 22 is along here. So I'm going to go across on my graph, and I'm going to figure out where does my line hit. My hit 22. And then I see that it hits about here. As you can see, if I was doing this, I would actually use a ruler, but I don't have a ruler, but I have somebody's book. So you can't see me lining it up, but I'm lining it up and then drawing a straight edge. Fortunately, the joys of working on a computer means that it's hard to get it perfect. So at about 31 hours, so milk will keep fresh. For about 31 hours at 22 degrees Celsius. So that's room temperature. So if you leave your milk on the counter for 31 hours for just over a day at room temperature, it's probably still okay. So then at 4 degrees, we're going to look, so 4 degrees is about here. So again, we're going to follow along until we hit our point. So our point here is about here. So that is 52, 54, 56. So, and it will be for about 56 hours at 4 degrees Celsius, which is generally how cold fridges are. So that means your milk generally, so 56 hours is about 2.5 days. Whether or not that's actually true, I'm not sure if that to me, my milk generally is better than 2.5 days, but anyway, that gives us a rough idea about how to use a graph to answer these questions. Okay, so let's do some more general practice questions, opposed to just looking at half-lives and doubling time. So for number 1, we want to complete the table of values using values of x between -3 and 3 inclusive. So from -3, -4, -5, -6, -7. No, sorry, -3, -2, -1, 0, 1, 2, and 3 is what we're looking for. So we're going to do that for both y equals 10 to the exponent x and y equals 1 over 10 to the exponent x. So this is we're going to use a little bit of our exponent laws from before, from lesson 4. So when I have x is equal to -3, so then y is equal to 10 -3. So that's going to equal to 1 over 10 to the third, which is 1 over 10, or sorry, 1 over 1,000. Then 10 to the exponent -2 is equal to 1 over 10 squared, which is equal to 1 over 100. 10 to the exponent -1 is equal to 1 over 10 to the 10 to the 1, which is equal to 1 over 10. 10 to the exponent 0 is equal to 1. 10 to the exponent 1 is equal to 10. 10 to the exponent 2 is equal to 10 squared is equal to 100. 10 to the exponent 3 is equal to 1,000. Okay, so then if we do it, make a table of values for y equals 1/10 to the exponent x. So again, -3, -2, -1, 0, 1, 2, 3. So 1/10 all to the exponent -3. Remember, with negative exponents, that means that we're going to, a negative exponent means we have the reciprocal. So that means we have 10 to the exponent 3 to our positive exponent. So that is 1,000. So 1/10 to the exponent -2 is the same as 10 to the exponent 2, which is 100. 1/10 to the exponent -1 is equal to 10 to the exponent 1, which is 10. 1/10 to the exponent 0 is equal to 1. 1/10 to the exponent 1 is equal to 1/10. 1/10 to the exponent 2 is equal to 1/100th. And 1/10 to the exponent 3 is equal to 1/1000th. So there we go. We made our table of values. So part 2 is, how are these values in each table related? Well, if we look at them, they are the same values, but in reverse order. We're looking at the same numbers. So in y equals 10 to the exponent x, we are starting really small and getting bigger. And in y equals 1/10 to the x, we are starting big and we are getting small, but our values are the same. So for part 3, we're asking you to graph each function. And again, we're going to use Desmos. So with Desmos, we can do 2 on here at once. So we have y equals 10 to the exponent x, and we can see it's shown us that purple line. And then we can have y equals, I started on a new line here at 2, y equals 1/10, so 1 divided by 10, all to the exponent, all to the exponent x. You can see again, we get another line. Now, these lines are super, super close. They're really, really hard to see. So if I go to this little wrench tool and I get my settings, I can change my axis. So I can say that I don't want it to go all the way down to -179. I want it to be at negative, say, 20. And I up to positive 20. And now I can see a little bit more. And the same thing with my y-axis. I don't want it to go up so high. I'm going to say, well, the negative doesn't matter because I don't have any negative values. But instead of going all the way up to 191, I'm going to say, well, let's just go up to 100. And then we can see it's still the same shape, but we can see it a little bit more clear because we weren't just zoomed out so much. But we still have the same shape. So, and we can see here, I'm going to change the color of my line just so that it's a little bit more obvious. So we have y equals 10 to the exponent x. We use this purple line, we can see that it's growth, and y to the 1/10 to the exponent x is my orange line, and we can see that it's decay. But it's symmetrical because they are opposite each other. So here, if I'm just going to sketch that, we can show that that's growth and that this one is decay. It's okay if your numbers are not perfect. Just getting a sort of a general shape is really good. As you can see, my growth will work much better than my decay, just the way my hand is. And that you don't cross over your x-axis. So again, how your graphs related, they're mirror images of each other. It's because their bases are kind of related. Their bases are reciprocals of each other. All right, so for number 5, it says identify the type of growth, linear, quadratic, exponential, illustrated in each graph. Justify your answers. So part A, looking at the graph is going to make this much easier than just listening. But here, A, we can see we have this curve where we don't go over x, we cross our y-axis at about 1, and then we increase. So A is exponential. B, we have a straight line. So straight line is linear. C, we have that U shape. So that's a parabola. So that's exponential. Oh, sorry, not exponential, quadratic. D is a little bit tricky because we are now in the negative values, but still you see we don't cross the x-axis, and we still, now we're at -1 in where we cross our y-axis. So this is still exponential. It's just that we have a negative reflection. But it's still the exponential shape. And E, again, we have a straight line, so it's linear. So being able to identify those is important. It's just helpful for you to know what tools you need to use. And number 6, says identify which graph represents each relations, justify your responses. So we have 4 graphs on 4 functions on a graph, A, B, C, and D. They're different colors. And we can see that they're all exponential. They all don't cross the x-axis. They all go through 0.01. They all have that general curve. So we need to figure out which one is which. Some of them are exponential and some of them are decay. Or sorry, some of them are growth, some of them are decay. So C and D, we can see both start off small and get bigger. So C and D are both growth. And A and B start off big and go small, and so those are decay. So that means growth means that our base needs to be bigger than 1, and decay means our base needs to be between 0 and 1. So a decimal or a fraction. Then we can look and we say, well, the farther away we are from the axis, the wider we are, the slower we increase, the smaller our base is. So here, C is bigger than D, right? Our base is going to be bigger. So that means that our C value, our base value has to be bigger than D. So if we look on our options, we have part B is y equals 2 to the exponent x. So that's going to be a growth because we have a base greater than 1. And part D is y equals 10 to the exponent x. And that's also going to be growth because we have 10 is base greater than 1. And then C, our base for 10, so our base for D is 10, whereas our base for B is 2. So that means that 10 to the exponent x is going to happen faster. It's going to grow faster. So that's got to be graph C. And that means that for graph B, it has to be D. And then similarly, looking at our decay values, we have part C, which is 1/2 to the exponent x, and part A, which is y equals 0.1 to the exponent x, which is also could be 1/10 to the exponent x. And so the same idea, well, this we know is decay because it's a fraction. And 1/2 is farther away from 0 than 0.1. So that means that we are growing slower or decaying slower. So that's going to be part A. And then y equals 0.1 to the exponent x is going to be B. So using that process of elimination of the parts that you know is how you can figure that out for this type of question. All right, so let's quickly consolidate as we wrap up. Our highlights from today's lesson are that for exponential functions, our equation is y equals a to the exponent b, y equals a times b to the exponent x, where b is our base. It can be any positive number except 1, and a is our scalar, which is any non-zero number. If we have our base is greater than 1, we have exponential growth. If our base is between 0 and 1, we have exponential decay. When a is equal to 1, all of our exponential graphs will go through the point 0, 1. And we never have an x-intercept. Y never equals 0. So we're always above the x-axis or below the x-axis if we have a negative reflection. All right, so now hopefully you can visualize and sketch exponential graphs. Hopefully you can explain how to identify exponential equations. And you can explain the similarities and differences between exponential growth and decay. If you have any questions, please as always reach out to me. You can call me at the office at 807-737-1488, extension 2209. You can also call toll free at 1-800-667-3703. Send me an email at bronwyn.slate@nnec.on.ca. Connect with me through Facebook, where my name is B. Slate Wahsa. Watch all the replays on YouTube at B. Slate Wahsa. Slow things down, pause them, take a break. Understandable, it's a lot of information that we cram into this hour. My office hours are Monday through Friday, 9 a.m. to 3 p.m., except on Thursdays where it's actually 10:15 to 4:15. But no worries, reach out to me and I'll get back to you if we don't connect. Thanks so much for joining me. I hope you have a lovely day. Miigwech.